Hey, today we're going to look at another technique of integration known as trigonometric substitution. Let's look at the integral of 1 over the square root of 9 minus x squared dx. The unpleasant part about that is the square root in the denominator, and ideally we would love it if we could somehow make that go away, which we could if 9 minus x squared was a perfect square. Now, very shortly, I'm going to give you just a straight out do this kind of algorithm that won't require you to sort of work your way through the reasoning behind it. But I want to motivate where that comes from. So the work that we're about to do is not work that you're going to do every time you do one of these problems. It just explains why the next step is what it is. And so maybe it makes sense to do it off to the side over here. We start with the trig identity, sine squared theta plus cosine squared theta equals 1, which we can rewrite as cosine squared theta is equal to 1 minus sine squared theta. And the thing to notice here is that 1 minus sine squared theta has a certain structural resemblance to 9 minus x squared. They're not the same thing, but they resemble each other. And the beauty is 1 minus sine squared theta is a perfect square. It's the cosine of theta squared. And so this is sort of strategically where we're going. One of the obstacles in trying to make 9 minus x squared look more like the 1 minus sine squared theta is the 9. We have 1 minus something squared on the right and 9 minus something squared on the left. But that's not too hard to deal with algebraically. In particular, we can factor a 9 out of the part underneath the radical there. 9 minus x squared is the same thing as 9 times the quantity 1 minus 1/9 x squared. Check, distribute. 9 times 1 is 9, and 9 times 1/9 x squared is just x squared. And so we end up with, if you distribute there, 9 minus x squared. So we haven't changed anything by factoring out the 9. And so what we really want is we want the 1/9 x squared to be equal to sine squared theta. Because if that were the case, we'd have 1 minus sine squared theta there instead of 1 minus 1/9 x squared. And 1 minus sine squared theta is the perfect square cosine squared theta. And it turns out that with just a little bit of algebra, it's not hard to find a way to make the 1/9 x squared equal to sine squared theta. In particular, if we let x be 3 sine theta, then we get that 1/9 x squared is sine squared theta. Okay, as I described, that logic was just sort of motivating why we do the next step. But the next step is we let x equal 3 sine of theta. And before we see what happens and where that gets us, let me just compare this to substitution. In substitution, you make up some new variable like r, or it could be theta, and you set it equal to some function of x. This is not that at all. This is more of a reverse substitution. You let x be some function, in particular a trigonometric function, of some new variable. So it's quite different than what we've been doing with substitution. It is in some ways the opposite. I like to think of it as a reverse substitution. So we let x be 3 times the sine of theta, and I'll give you mechanical rules for how to decide on that a little bit later on. Then taking the derivative with respect to the variable theta, we get that dx d theta is 3 times the cosine of theta, or in differential notation, dx is 3 times the cosine of theta d theta. And the beauty here is that we can now rewrite our original integral entirely in terms of the new variable theta. And what I've done here is I've taken this expression right here, and in particular, I've taken the x right here and replaced it with 3 sine theta because x is equal to 3 sine theta. And I've taken the dx that we have here and replaced it with 3 cosine theta d theta because dx is equal to 3 cosine theta d theta. And now I have a brand new integral in terms of theta instead of in terms of x. I'm going through the algebra very slowly here because this is our first example. I've pulled the 3 cosine theta into the numerator, and then 3 sine theta all squared is 9 sine squared theta. And when we simplify in the denominator, we get in the denominator square root of 9 times 1 minus sine squared theta. And here's where the payoff is. We know that 1 minus sine squared theta is cosine squared theta, a perfect square. And so now we can take the square root of the denominator, and the square root of 9 cosine squared theta is 3 times the cosine of theta, and this of course simplifies. And after you integrate, you find that you get theta plus a constant. This of course can't be the answer. The problem is a question in terms of a variable x, and we have given an answer in terms of a variable theta, so we can't be done. We have to turn theta back into something in terms of x. Recall from the beginning that we set up x to be 3 times the sine of theta, and so x over 3 is the sine of theta after dividing both sides by 3. And that makes theta equal to the arc sine of x over 3. You could take arc sine of both sides, or you could just think about it. The angle whose sine is x over 3 is the arc sine of x over 3. And so our final answer, arc sine of x over 3 plus a constant. This was a fairly simple example of trig substitution. In particular, if you had recalled the derivative of the arc sine of x, you might have been able to do it by straight substitution, not just by trigonometric substitution. But still, we did it by trigonometric substitution just to show how the technique works. Before we move on to a slightly more complicated one, notice how important the dx is. The dx is the part that gives you this 3 cosine theta d theta, which ends up with a 3 cosine theta in the numerator. And if you're in the habit of leaving your dx's off, then you would be missing this 3 cosine theta in the numerator. And in the end, you wouldn't have that there, and you'd have the integral of 1 over 3 cosine theta, which is the integral, 1/3 times the integral of the secant theta d theta, and you get an entirely different answer. In this case, you could still do it. We've looked recently at the integral of the secant of theta, but there will be other cases where if you forget the dx and how it turns into some expression times d theta, then you're going to come up with an integral that is very, very difficult to work with, if not impossible. So you have to be a little bit careful about that. Okay, let's look at a similar but slightly more complicated integral. This one is more representative of what a typical trig substitution integral really looks like. Before we're done, I'll give you a set of rules for how to pick your substitution. But for now, if you've got something of the form a squared minus x squared, let x be a times the sine of theta, and that will work out nicely for you. Here we've got 9 minus x squared, which is 3 squared minus x squared. And so we'll let x equal 3 times the sine of theta. This once again gives us in differential notation that dx is 3 times the cosine of theta d theta. And we can now rewrite the entire integral in terms of the variable theta. You'll notice I didn't have to do the factoring out the 9 trick that I did to motivate where we got the 3 sine theta from. All I did was replace each x with 3 sine theta and replace the dx with 3 cosine theta d theta. And that gives us this expression here. Now in the denominator, where I have square root of 9 minus 9 sine squared theta, it's easy to factor out a 9. Which gives us this expression here. You see I've brought the 3 cosine theta into the numerator. And now we can take advantage of why we went to all this trouble. 1 minus sine squared theta is cosine squared theta. And we're now in good shape to take the square root in the denominator. And then we can do a little simplifying. And we end up with 9 times the integral of sine squared theta d theta. This is very typical to trig substitution problems. They basically have 3 parts. We just completed the first of them. There's no way around it. Trig substitution problems take a while. There's a lot to do. What we've done is we did the trig substitution, did a bunch of work, most of it trigonometric or algebraic, and came up with a new integral. The part that was missing from the last problem that was a little bit too simple is that now there's some integration to do. Now that we've come up with a new integral, how do you integrate sine squared theta d theta? And the answer is we've studied that already. This is an even power of sine. You need a trig identity. And the trig identity is that the sine squared theta is 1/2 times 1 minus the cosine of 2 theta. We can certainly pull the 1/2 outside the integral, and then we can do this integral by substitution. If we let r equal 2 theta, then dr is 2 d theta, and dividing both sides by 2, we get that 1/2 dr is equal to d theta. Rewriting the integral in terms of r, the cosine 2 theta becomes cosine of r, and the d theta becomes 1/2 dr, and I've pulled the 1/2 out in front of the integral. After we integrate, you have to be a little bit careful. The integral of 1 dr is r, so there's lots of variables floating around, but we're integrating with respect to r. And so we get 9/4 times the quantity r minus the sine of r plus a constant. R is equal to 2 theta. And after we simplify, we get 9/2 theta minus 9/4 the sine of 2 theta plus a constant. We've just done the second third of the trig substitution problem. They really do fall into 3 parts. The first part was the actual trig substitution. The second part was integrating the thing you come up with. But now we have an answer in terms of theta, and we want an answer in terms of x. And so we have to take this and try to turn it back in terms of x. And let's magically make a little room here. Recall that we started with x equals 3 times the sine of theta. So the first part, figuring out what theta is, will be just like in the last problem. Just like in that problem, we get that theta is the arc sine of x over 3. But now we also need to know, what is the sine of 2 theta? And for that one, well, I promised you that there were 3 trig identities that you would need to know. We had explored 2 of them to some degree, but sine of 2 theta was the third. And the trig identity is that the sine of 2 theta is 2 sine theta cosine theta. You now make yourself a right triangle, assign one of the non-right angles the value theta. We know that sine of theta is x over 3, so opposite over hypotenuse is x over 3, so we can make this side x and this side 3. And then if we call this side a, we can use the Pythagorean theorem to say that a squared plus x squared is equal to 3 squared. Or solving for a, we get that a is the square root of 9 minus x squared after throwing away the negative square root because it's a length. That should give you a good feeling because the original integral had a square root of 9 minus x squared in it, and so it makes some sense. It seems reasonable that the result should have a square root of 9 minus x squared in it. Okay, we're nearly done. We already know that sine of theta is x over 3. From our right triangle, we can compute that the cosine of theta is adjacent over hypotenuse. It's the square root of 9 minus x squared all over 3. And then using the identity that sine of 2 theta is 2 sine theta cosine theta, we're ready to write the answer to the integral, ready to finish the problem. In particular, the 9/2 theta is 9/2 the arc sine of x over 3 because we already determined that theta is the arc sine of x over 3. And then we're subtracting 9/4 the sine of 2 theta, and the sine of 2 theta is 2 sine theta cosine theta. And the sine of theta is x over 3, and the cosine theta is square root of 9 minus x squared all over 3. And I better not forget to add a constant at the end, because after all this work, it would be a shame to lose a half a point. Still going to lose a half a point anyway, though, if I don't do a little simplifying. So let's simplify this answer and then really be done. And all that really needs to happen is to muddle through the constants that we have there. We have 2 3's in the denominator, that's a 9. They cancel with the 9 in the numerator. And we're left with a 2 in the numerator and a 4 in the denominator. That's a 2 in the denominator. And so we get this result here after all that work. This is the solution to the original problem. Okay, that's trig substitution. You're certainly going to need some practice. The next video will just be doing some examples. You can't rush through these. There's no way around it. Trig substitution has a lot of parts to it, and so there's lots to do. They're going to take time. Do it slowly and carefully, and it'll come out better and probably quicker than if you try to rush through it. I just wanted to give you one last bit of information before we called it a day and moved on to the next one when you're ready. As we've already seen, if you have something of the form a squared minus x squared, you can let x equal a times the sine of theta and use the trig identity 1 minus sine squared theta equals cosine squared theta. What we haven't yet seen is that you can also use trig substitution if you have something of the form a squared plus x squared. In that case, let x equal a times the tangent of theta, and you'll find that you'll be able to use the trig identity 1 plus the tangent squared theta is equal to the secant squared theta. And finally, the last case, if you have something of the form x squared minus a squared, which is very different from a squared minus x squared, then you can let x equal a times the secant of theta and use the trig identity secant squared theta minus 1 is equal to tangent squared theta. Okay, that was trig substitution. As I mentioned, you could probably try the homework. You could probably do at least the first 2 problems. With that last bit of information that I gave you, you could probably do all of them, but it might make sense to watch that second video before you tried at least the last few problems on the trig substitution homework, and maybe even the first couple as well, depending on your schedule and how brave you feel. They're not so bad. No particular single part of a trig substitution problem is especially hard, but no particular part is especially easy either. There's work all the way through, and there are no real shortcuts. So, gotta love it. Have some fun. See you soon.